Alright, here's number 7 from the 2010 AP Physics B exam. This is primarily a photoelectric effect problem. We've got light shining on a metal surface. We're going to eject electrons with a specific amount of kinetic energy. We know the wavelength of the incident light. We're going to lead off trying to figure out the frequency of the incoming light. This isn't photoelectric effect part yet. This is simply what is the frequency. And as long as you recognize the wave speed equation, c equals f lambda, we can find that frequency. It's just going to be c divided by lambda. C is the speed of light, 3 by 10 to the 8 meters per second. And lambda is the original 400, but it's 400 nanometers, so it's by 10 to the negative 9 meters. Toss in your calculator, you're going to get 7.4 or 7.5 times 10 to the 14 hertz. B. What is the work function of this metal surface? Well, let's look at the photoelectric effect equation. Before I do that, I want to work over here, so I'm going to kind of do some wizardry and hide this. Alright, good enough for me. The photoelectric effect equation is this. The input energy of the photon, HF, that's the light, will equal the work function of the metal, the minimum amount of energy required to eject electrons, plus any additional energy the electrons gain. We often write Ke max because we usually deal with the maximum speed in which an electron can gain, even though some might end up having smaller energy that it absorbs. We know Ke max, that was given. We know F, so we can find HF. Phi is the work function. That's what I'm looking for. So my work function is going to be my incident energy minus the kinetic energy. Which means it's going to be, well, I'm going to use, this is in joules, so I'm going to use the H version of joules, or Planck's constant that's in joules. So that's the 6.63 times 10 to the negative 34, and that's a joule second, times the frequency I just calculated, 7.5 by 10 to the 14 hertz. Then we're just going to subtract that given kinetic energy. We will get an answer in energy in joules, and that's going to be 3.9 times 10 to the negative 19 joules. That's it. That's the answer to B. Let me clean this up real quick. Get it out of the way. C wants us to determine the stopping potential for the emitted electrons. That basically means if we were to put this in an electric field, how much voltage or potential difference between where the electron is and where it wants to go, how much needs to be there to stop the electrons? Or how much work does the electric field need to put in to stop those electrons? Well, if you put in less energy than the kinetic energy of the electrons, then the electrons will still travel with a little bit of speed. If you put in more energy than the kinetic energy, then you're stopping those electrons and you're basically, like, I don't know, making it even harder for them to leave. So the stopping potential is always going to be equal to the amount of energy required to get rid of the kinetic energy completely. Or the work due to the electric field needs to equal the kinetic energy of the electrons. But that's not stopping potential, that's the work. Your stopping potential is voltage. Voltage is equal to work over charge. Or voltage times charge is equal to work. So your stopping potential times the charge of one electron must equal the kinetic energy of one electron. Therefore, our stopping potential is going to be our kinetic energy over charge. That kinetic energy is what was just given, or earlier given, 1.1 by 10 to the negative 19 joules. Charge is 1.6 by 10 to the negative 19 coulombs. That is the charge of one electron. Toss parentheses down here so you don't screw up your math. And we're going to get a stopping potential of a relatively tiny value, 0.69 volts. Now we need to calculate the momentum of the electron that has this maximum kinetic energy. Now we could derive an equation here. I'm not gonna. I'm going to go through the steps and, I guess, show you the derived equation. Really, in order to know the momentum of a particle, anything with mass is mv. So I need to know the mass and I need to know the velocity. Now, the mass of the electron is easy. I can look that up in my tables. It's the velocity of the specific electron that's going to be taking an extra step. And we're going to find that from the kinetic energy equation. Kinetic energy is 1/2 mv squared. Now I could isolate v, plug it in for here, and then make a nice, good, fun-looking equation. I'm not going to do that. I'm just going to find v first and then plug it in here and find momentum. So the velocity of the electron is going to be 2 times the kinetic energy divided by the mass of the electron, and I'm going to square root that. So I'm going to take radical 2 times 1.1 times 10 to the negative 19 coulombs, or joules, I'm sorry. I'm going to divide by the mass of one electron. That's the 9.11 times 10 to the negative 31 kilograms. That's something you look up. We're going to figure out that velocity. Ends up being 4.91 times 10 to the 5 meters per second. Now I'm going to take that and I'm going to plug it in for velocity over here to show the momentum of this electron is 9.11 times 10 to the negative 31 kilograms times 4.91 by 10 to the 5 meters per second. Do some calculator wizardry and we're going to get 4.5 by 10 to the negative 25. Standard units, so it's going to be a kilogram meter per second. And that is the answer to number 10, or letter 10, and the completion of number 7.